All Happy Inventor videos are for educational purposes only. Mr. Ragnar is neither a patent attorney nor a licensed patent practitioner. Therefore, no portion of this or any other Happy Inventor video should be considered legal advice. If you have a patent need, you are advised to contact a licensed patent professional. Welcome. I'm Gary Ragnar, and you are watching the Happy Inventor channel. And today we have a very unusual invention for you. And it's not unusual because it's a strange invention. It's unusual because the path between idea and marketable product has been very strange indeed. I've been inventing for many years and have almost 50 patents and 20 patents pending at the present time. And I've never seen an invention take this kind of convoluted path that I'm about to present to you. So let's take a look at this strange invention and just enjoy it. The invention I'm going to present to you today is not particularly interesting as far as inventions go, but it is interesting for you, the inventor, because it shows how the 7 steps of inventing can be rearranged in very strange order to provide you with a logical path to making money with an invention. This particular invention or idea came from an email that I received from a multinational corporation. This is unusual because most large corporations do not want to deal with a private inventor or even with intellectual property from other companies. It's made here or nowhere is the attitude of many large corporations. As the companies get smaller, they're more open to taking a look at intellectual property from outside their company. Here's the drawing that UTB Envirotech sent me. It is actually an invention itself, other than they didn't know how to implement this expanding and retracting hose that's in the center. And let me describe what this is. This is a water treatment plant where they have a floating skimmer, decanter is what they call it, where water is always flowing in and kind of skimming the top surface, and then that goes down this drain and out. And what they want is this floating decanter to be able to rise and lower with the water level so that it's always functioning the way it's supposed to be functioning. However, notice this is a 12-inch diameter hose, and no one makes anything like that. And besides that, this is actually has the pressure on the outside of the hose, where nearly all other hoses made have the pressure on the inside. For example, a garden hose, when you turn the water pressure on, the water pressure is on the inside, not on the outside. In this situation, you have all this water on the outside and water drain down the middle, but it's not going to necessarily be full all the time. They've drawn it full, which is interesting, and maybe they can maintain that filled state. But if this ever goes empty, this hose has to be able to withstand all that water pressure on the outside. So there was an invention that needed to be done here. And they gave me the idea for this, that they need a hose that can fit in this basically water treatment plant. And so my goal now is, how do I build this hose so that it can handle the water pressure on the outside without collapsing and still be able to extend and retract about 3 times, because here they have 2 meters for the lower level and 5 to 6 meters as the high level. So that's about a 3x expansion ratio for this particular hose. I did not have the equipment to build this very large diameter extendable and retractable hose, but I did know a company that had equipment that could build hoses that size, and I had dealt with them about a decade ago when we were trying to make a particular type of extendable and retractable hose. But unfortunately at that time, they were one of those companies that if it's not made here, we don't want it. And even though we were trying to contract with them to build us a hose, they got nervous that we would be competing with them and drop the whole ball. And so we had to go elsewhere. And this is an example of how many companies do not want to deal with you. So at this time in the process of not knowing where to go for that large diameter hose, I called UTB Envirotech, which I think I'll just call it Envirotech from here on out, and told them that we weren't really interested. Now another unusual thing happened. About a month later, called us and wanted to know if we had any good ideas for hoses, because they were looking for new technology and wanted to build out their product line for the future. And I was kind of shocked because this is a complete turnaround from 10 years earlier. And the reason for that was they had a new CEO. And he was actively looking for products, new products specifically, that were compatible with their product line. So now I had a company on one hand that wanted me to invent a hose that could extend and retract underwater and work in an environment where it had a negative pressure inside. And then I had another company looking for inventions that they want to license so they can make new products. So if all of a sudden I've got step 6 done in the invention process, I've got a buyer and I've got a seller, and I'm in between creating the intellectual property. This is kind of unusual to go from idea, step 1, jump to step 6, create the market for it, and now I'm going to go back and do step 2 and actually invent the product. I haven't even done that yet. I've looked at it, but at this point I'm not sure that that particular hose can be done. And so we're going to take a look at it now. I'm going to go about the actual invention process and see if I can create a working hose that will provide Envirotech with what they need. One of the first things you should do before you start inventing something is make sure you understand what you want the invention to do and how you're going to get it to do it. So with our problem here, where we have an expandable and retractable hose in a water filtration system, we want to identify what factors that hose has to have so that when we go about designing it, we can design those properties into that hose. All right, notice 2 meters to 6 meters. That's about a 3x hose. It has to expand 3 times. But notice the way this is drawn, the fixed discharge pipe actually takes up about half of the 2 meter level at the bottom. So that means that this smaller compact area is only going to be maybe 1 meter long, which means to get to 6 meters, we're going to need about a 5x stretch in it. This is at the limit of materials science, and I'm not even sure if that's possible. But it is possible that we could actually lower this discharge pipe down further so that we have a little bit more room to put our retractable hose when it's in its retracted position. Also, we know that we need some radial strength in case the water drains out of this pipe or flexible hose so that the water pressure on the outside doesn't crush it. We're going to have to look at that and make sure that we take that into account. We also have to make sure that the fabric and the waterproofing on the outside can handle this pressure, as well as the structural part that provides that pressure resistance. So let's take a look at how we can design a hose that will do all these things. Here we see one of my patents that issued back in 2014. And it shows a number of different extendable and retractable hoses that could possibly be used for our water treatment plant hose. Notice that the reinforcement in this case and this case is on the inside of the spring coil. Now the spring coil is actually what is going to provide our radial strength, because this interior fabric really can't support any weight in itself on the inward direction. These hoses were designed to have pressure on the inside and forcing outward, which is completely different than our situation where we have water pressure on the outside of these hoses pushing inward trying to crush the fabric. So we need actually something more alike to this one on 7C and 7D, where the reinforced fabric actually goes on the outside of the spring coil and is supported by the spring coil from being crushed inward by the water pressure on the outside. But there are some issues with the physics of this, and I'm not absolutely sure if that is going to work, or not necessarily whether it will work, but how it will work. And so I believe what we should do now is actually skip step 3 and not do a patent search, which would include my own patents, but build a prototype to test some of the physics involved with this type of structure being underwater and also being situated vertically in that water. Before I start building and testing a prototype hose, I want to point out a few things in here about the physics that we will be working with. For one, the buoyancy on this hose itself should be close to 0, because the bottom of the hose is actually connected to this fixed discharge pipe. And the fixed discharge pipe is actually what is supporting the buoyancy of all this air column, because the water pressure underneath this discharge pipe is what has the high pressure, and then you have low pressure air above it. And so the buoyancy is actually on the fixed discharge pipe. However, if we use the convoluted shaped hose that I just showed you in my patent, then those convolutions will have different pressures on them, and there will be a upward and downward force on every one of those pleats. Thus, there will be a difference in pressure as you go up the hose towards the surface. My thinking is that this pressure difference is going to result in a force wanting to extend this retractable and extendable hose, and so it will naturally want to extend and be relatively taut at the bottom and loose at the top. Now, I don't know that for sure, and that's why I'm going to build a prototype now, just for the specific purpose of testing the physics of what's going to happen when this type of flexible hose is underwater and oriented in a vertical position. When you're building a prototype, you have to keep in mind why you're building that prototype. For example, if you're building it for an investor or a licensor, you want to have that prototype as polished as possible, because they're not going to be able to imagine what it might look like. You're going to have to show them what it does look like. However, if you're building that prototype to test the physics or the operation of the product, it can be as crude as you want as long as it still works. And so I happen to have this air conduit, which is actually 12 inches in diameter, which is the diameter we're interested in. But the material is pretty flimsy, though fairly strong. But remember, we're going to have hundreds and hundreds of pounds of pressure pushing on this conduit once it's underwater in a water treatment plant. And so it's definitely not going to be strong enough. We're going to need stronger material. And also, the wire coil in here is just really wimpy. Just a few pounds of force makes it squish and deform. And it's certainly not going to hold up to the high pressures of an actual water treatment plant. But for our test, it's going to probably work fine. I'm going to take the end of this and cover it with duct tape to seal it off so that it's waterproof. And then I'm just going to take it and stick it down at the bottom of a bathtub so that it's a couple feet underwater. And we'll be able to test at that depth what the water does to these convolutions, what the fabric does, how much these rings deform. We're going to be able to test a lot of different things, and hopefully we'll be able to get enough information out of that to make a very good educated guess at how this product would work if it were beefed up and the wire was made stronger and the material here was made thicker, so that everything was stronger in the final run. Now, to help it hold its place down in the bathtub, I'm going to be taking this can, which is full of iron weights, and so this thing weighs about 50 pounds, and I'm going to take it and turn it upside down in this to hold it to the bottom of the tub. And I'm hoping it's heavy enough to actually hold it to the bottom of the tub. If not, I'm going to be with my arms down there pushing it to the bottom to help hold it at the bottom of the tub. So let's go ahead and build this prototype, and then I'm going to go and test it in a bathtub, and we'll see what happens. All right, here we go with the test. I've got the tin can in here that weighs 50 pounds. I have it upside down so the big side is down and the little side is up, so that it doesn't interfere with the coils and the fabric as much as possible. And I'll also have the duct tape across the bottom to hopefully seal that and keep all the water out. So let's go ahead and put it in some water and see what happens. Alright, it's in there. Let's move it over so you can see it a little bit better. Coils seems to stay nice and even. You can see the water pressure is pushing in between the coils, which is pulling the coils together. But there seems to be some buoyancy too. It doesn't take much force to spread out those coils because there's some air in between each one of these layers, and it's providing a little bit of lift on every coil. It seems to be supporting it okay. Let's see what the depth of the water is. 14 inches of water. Not a great amount of water, but this is, remember, has very weak wires in it, and I was afraid that would be the most problem, but it appears to work really well. It goes up and down, stretches with a little bit of force, all seems to hold together. Doesn't seem to be particularly sensitive to deformation. It's got air down the center, it's still round. It's actually looking good. All right, let's go on. Well, we learned a lot from that experiment. We learned, one, that the duct tape will seal the end of a large tube and let very little water in. In fact, I didn't even get any water on my weights. But what we really wanted to know was what happened with all this fabric and coils. And we found out that the water pressure actually wants to push this fabric in, which tends to pull these coils together. And so the first force we noticed was that one wanted to retract the hose. That force, the compressive force on the fabric, wants to pull the ends of the hose together. Now besides that, we also had a buoyancy force. These coils have actually a little bit of air in there, and that gives a little bit of buoyancy for every single coil. Now where the force in between here really doesn't add, because if this one has the same force as this one, you just have the same force across both coils. But the buoyancy is adding as you go down every coil. So the more coils you have, the more buoyancy you have. Also, the pressure that's in here goes up as you go deeper and deeper. So what I believe is going to happen is the buoyancy force and the force in between pulling the coils together is almost going to balance out, and we're at the very top of the hose. There's almost no pull either down or up with the hose. This is actually good because we don't have to worry about the flotation of that decanter at the top of the hose. It's just going to float there, and it's not going to be pulled on all that much. Now, there is a problem though. Even though this hose seemed to have no trouble at 15 inches of water, and probably about 12 inches depth, actual real depth for the coils, that's only about 1/15 to 1/20 the depth that we're actually going to use these hoses at. But that only means we have to make this wire 15 to 20 times stronger. And that's easy to do. This is mild steel. It's not very strong at all. And you can take, for example, a piano wire and use it the same diameter, and it will be 5 to 6 times stronger than this particular wire here. And if you double the diameter, you would increase it 4 more times, and you'd be up to 20 times stronger for only a little bit more larger diameter. And as far as the fabric is concerned, it was not even close to failing under 1 foot of water, obviously. But we can easily strengthen this up because this hose here is actually 1 foot long right now when it's compressed or retracted, whichever one you want to call it. But it extends out to 15 feet. Now underwater, when you're having pressure in here, that 15 feet is probably going to be more like 10 feet. But still, a 10x hose is well beyond what we need for our 5x that we saw before, or even a 3x. So we have plenty of room for increasing the thickness of this fabric in here to make it as strong as we need it. And so I think we're done with the inventing part. We have figured out what we need and how we can do it. So let's move on to step number 3, doing a patent search. We want to do a patent search to identify any prior art that might give us problems in obtaining a patent on our invention. In this particular case, I'm going to be looking at my own prior art, which I have several patents dealing with hoses that expand and contract. And also I'll be looking at different hoses that are actually on the market. They're prior art also. Obviously you can't get an invention on something that's already done. The initial problem I see is that a hose like this, if the construction is just beefed up a little bit, it might actually be a workable hose. And so if you remember, for inventions and patents, you actually claim the structure. So if the structure is the same, but we just beef up the strength of materials and things like that, that doesn't count as a new invention. It's more technical issues that you're solving. And the patent office will not allow you to get a patent on that type of improvement. So we're going to be looking at all this intellectual property and seeing if it makes sense for us to actually file a patent application. And a patent search is very important because it can save you a lot of expenses on patent applications that you don't really want to even do. So let's now take a look at some of the prior art. I have finished the patent search and have 8 patents I want to show you. Before that, you may have noticed that I'm not showing the detailed process of doing each one of these invention steps. And this is on purpose, because this episode is actually dedicated to trying to teach you the interaction between these steps and not necessarily the specifics of doing each step. For example, with the prototyping, I didn't even show you how I constructed the end on that prototype. I just showed testing it and the results of that test. Similarly, here with the patent search, I am just showing you the results of the patent search and not the actual process of doing the patent search. So let's take a look at this first patent, which is by me and Robert de Rochemont. And it shows one of the first, if not the first, extendable and retractable hoses for pressurized water. And it was designed to provide both a garden hose that could extend and retract and a vacuum cleaner hose that could extend and retract. Now they both worked on the same hydraulic principle but in opposite directions. However, both of these hoses could be adapted for our water treatment plant hose, and thus potentially could be a design for the hose that we use for the water treatment plant. Besides various hose designs, there's also various processes out there that can be used to build these hoses. This particular patent is for an extendable and retractable hose using a knitted reinforcement. This page we've seen before, and it provides a reinforced hose that could be used for a water treatment plant. And here is another hose making process, actually again my patent, that could be used to make hoses for a water treatment plant. Now we're going to go on to other people's hoses. Going back to 1943, it was more for having a flexible hose as opposed to being able to retract, but if you forced it, it could be compressed, as you can see in the next page, as in right here. Here we see an extendable and retractable hose or tubing that has a construction very similar to the yellow hose we used for the prototype. However, the yellow prototype actually used just a strip right over the wire. This particular design uses a long, wide strip that covers not only the wire but extends to the next wire. And literally this hose is made by wrapping this strip of plastic around the wire and then over the wire, producing a sealed tube in the process. Our yellow prototype hose was actually made by forming a complete tube and then wrapping the wire around with a small black cover that attached to the tube. The two hoses look the same from the outside but are quite different in their construction process and thus would constitute separate inventions. However, I was unable to find the patent for the yellow hose that I used for the prototype, though it probably exists, but maybe only in China. Finally, this is a design that's similar to the yellow hose, except it's a little bit more complicated in that it has 2 layers of fabric so that you can create an airspace for providing insulation. We don't really need insulation for our design because we are just transporting water down the center of the hose. So, from all these patents we can see that there's a lot of different ways we could make this hose for the water treatment plant. But that's not good for us because someone could just decide to do it one way, do it, for example, make this hose, or maybe they want to do it this way and they could make that hose, or maybe they even want to make it like this. They could do it that way, or they could go to one of my patents and decide, oh, this is the way to do it. And so with so many options, the patenting process is kind of circumvented. Can I get a patent that will be useful? Well, as an inventor, having a whole bunch of different ways of doing it is okay, but you really want to have the patent on the best way of doing it. And by best can mean a lot of different things. Best might mean the cheapest way of doing it, or the strongest way to do it, or the longest lasting way to do it. And so you have to decide, is it worth actually doing a patent here? And that's the next step. We're going to look at this prior art and try and decide, are we actually going to file a patent application for a particular hose structure that can be used in a water treatment plant? Or are we going to think of more creative ways of making money with the knowledge that we have from these particular hoses? So that's what we're going to do next. Let's look at patenting. So should we do a patent application or not? There's a lot of prior art out there and many different hose designs that could possibly be used for our water treatment plant. And we're fighting against all those other types of hoses to compete with anything that we happen to invent. For example, this particular hose that we used for our prototype, it could be modified to work in the water treatment plant. However, this particular design requires a very thin wall of material. This yellow fabric is only 6/1000ths of an inch thick. It doesn't take a whole lot of wear on the inside of this hose to wear through and fall apart. And so is there a better way to build a hose? Or which hose out there is the best way to build it? Consider the situation we have with this prototype hose. This fabric in between the coils, when pressed, is actually the weight of the water on it that it has to support. And for example, if the spacing between the coils is 4 inches, and you look at a 1-inch strip between the coils, that 1-inch strip is holding up 4 inches of water. And if you're down 16 feet, the pressure there would be around 8 pounds per square inch. So 4 inches at 8 pounds per square inch would give you 32 pounds of actual force that this fabric would have to hold up. And each side holds up half of it. And so you would have approximately 16 pounds of force on each end of the material, which is well within the strength of this material here. So this material can go down to 16 feet of depth in water and support itself if it has a spacing of 4 inches. Now if you go out to 8 inches, the pressure would double, plus you have an angle factor here too. With the angle here, you'd have much more force as opposed to here, where the angle of the fabric going into the curve is much less, and you would have to take that into account. But the fact is that if we put the coils closer together when we're manufacturing it, we are literally reducing the amount of force on the fabric because there's less water in between. And in fact, if we go from 4 inches to 2 inches spacing, what happens? You have half as much water in between each coil, and so your forces are going to be reduced in half. And so now, instead of 16 pounds on each end of the fabric at each coil, you're going to only have 8 pounds. And even this thin 6/1000ths of an inch thick material is strong enough to support that very easily. And by moving the coils closer together, you now have twice as much coil material, and so your actual radial strength has doubled when you do this. So you've not only doubled the strength of your coil, but you've also reduced the stresses on the fabric in half. This is a very good combination, and so it makes a lot of sense to have wide spacing at the top of this type of hose where the pressure is low, and then the spacing much closer together as you get near the bottom. This will provide us with a hose that I hope we can actually file a patent application on and get a patent on. I finished the patent application and filed it with the United States Patent and Trademark Office. I did this electronically on my computer, didn't have to go anywhere to do it. And in return, they gave me a receipt showing that I have actually filed a patent application, and this officially makes my invention patent pending. Also notice that I've covered up many of the key identification numbers on this receipt, and you really don't want those numbers out in the public. You want to keep them secret. This video is getting quite long, and I'm going to wrap it up now with just a quick overview of what we've discussed. Now we are at the point where we have to start negotiating the different contracts and also figuring out how we're going to make money, either licensing, selling the patent application, or doing some other kind of contracting. So that's where we're at right now. That whole process has only taken about 2 weeks. The first week I was building prototypes and considering what kind of inventions could be done, testing the prototype and discussing it, and doing a lot of the videoing that you see now. The second week, Monday, I spent doing the patent search, and on Tuesday I did all the drawings for the patent application. I like to do the drawings first just because they give me a good idea of what the invention actually is that I'm trying to patent. And so on Wednesday then I started writing the actual patent application, and I wrote all day into the night and finally filed it at 3:30 in the morning. And the reason I stayed up so late is I wanted to have that patent application finished when I talked to which was at 10 a.m. But they had to cancel because of other obligations, which is not uncommon for a large corporation to cancel on you because the CEO is very busy with a lot of different projects. And the nice thing is that he has actually rescheduled the meeting for me to Monday, this coming week. And so he's still serious. He's rescheduling and keeping me abreast of what's going on. So on Monday, I'm going to be talking with him to find out if he has the equipment necessary to build this patent pending hose that I've designed, and also find out if that may not be the best way of doing it. That is the hazard. So we're going to be having to tweak the contracts a little bit to possibly make some money here, but that's the next goal. The future episodes I'm going to break down like this. Because I've skipped over the patent search process and the patenting process, episode 4 is going to be specifically on those 2 steps, and I'm going to show them in quite a bit of detail so that you can understand how those 2 steps are done. And then episode 5, I'm going to come back with what has happened with the negotiations. But I warn you, the episode 5 might not come out for quite a while, because while doing the first 5 steps can be done relatively quickly because they all depend on you, in this case I've done them all in 2 weeks, the steps 6 and 7 are not so quick because they do not depend on you, they depend on the other companies. And in my experience, 6 months is reasonable length of time. Sometimes it takes years to actually get the contract done. Which is amazing that it takes that long, but the larger the corporation, a lot of times the more red tape and the longer it takes. So with a large corporation, 3 months to get a contract is really actually very quick. In fact, some of the quickest ones I've ever done has been 3 months. So just a warning on that the update on this particular project may come in a much later episode, and we hope it turns out favorably. And if it doesn't turn out favorably, I'll also update you on that, just to see what kind of problems can happen when you're actually trying to make money from your patents. So keep inventing, and this is Gary, and I'm out.